Okay, thank you very much. I'm very pleased to be here today and delighted to contribute to this Open for Business event today. I'm going to talk about mathematical modelling, in particular with applications in transport and energy. And actually I'm rather conscious that when I was putting together this survey of work that we've been doing here in Cambridge for the last several years, that actually there are subsets of people here who must have seen some of this material before, possibly in this very room. But what I did remind myself as putting this survey together was just how rich these fields are of transport and energy now as they were in recent years, and especially now I think as sources of rich sources of mathematical models. And as I think we're sort of moving into this era of where data lies at the centre of many of engineering problems and solutions, I think this is a very nice time to revisit this material. So I'll talk about first of all about road transport networks, and I'll talk perhaps in two parts there. One is about using data associated with loop detectors, so fixed sensors in strategic highway roads like motorways and trunk roads, and secondly GPS trace data from buses. In fact, buses in Cambridgeshire. And then I'll follow with a discussion around energy networks and electricity networks in particular. So let's get started then, look at the loop detector. So these loop detectors are part of a system in the UK called MIDAS, so Motorway Incident Detection and Automatic Signalling. So this is a system put in across parts of the strategic road network in the UK, say on motorways and on some trunk roads. It was put in the mid-90s. What it does is it senses the flow of vehicles. In fact, per minute it's recording average flow and average speed of vehicles lane by lane. And using that information and sort of incident detection methods, machine learning methods, we would be able to detect the presence of reduced or unusual speeds and unusual flows on the road, for example indicating that an incident has occurred, and perhaps a minor incident has occurred, and then traffic upstream is forewarned of the incident by changes in the speed limits on gantries ahead, and so motorists no longer go ploughing into the back of minor incidents on motorways, creating major incidents. And this was a very successful system, but an archive of per minute measurements then became available, and somewhat later, maybe 10 years or so later, I was able to have access to that through a project funded by the Department for Transport. So there was a very messy data source. There's quite a large amount of data, and a particular sweet spot in that data set was the southwest quadrant of the M25. So just briefly remind you, so let's say clockwise from junction 9 near Dorking, clockwise past Heathrow, maybe to junction 14. So that particular section is very richly censored with these loop detectors. I believe they're every 500 metres. So per minute archive of flows and speeds. That's a terrific treasure trove for analysis of what's going on today's roads. One of the classic pictures in road transport is to look at these type of heat maps of speeds. So this was very striking when I drew this. I really didn't believe it at first, but this is what happens. So this is a speed map, so the colours go from red to yellow as the speed increases, and on the vertical axis is the loop detector, so around 60 loop detectors between junction 9 and junction 14, and per minute over one particular day, in fact a Monday morning. And these red streaking lines of low to moderate speed are the so-called stop-and-go waves that perhaps we're all familiar with now on motorways, where the traffic speeds up and slows down in sort of very peculiar method as you move on a trajectory from, say, the bottom left corner to the top right corner. You cross those waves in the speed. Another way of viewing that data, so this is just sort of taking raw data, or cleaned up raw data, and then visualizing it in I think useful ways. So this is in road transport it's called the classic speed flow relationship. So each little red cross is a data point specifying average speeds and average flow. I think it's aggregated over each of the lanes in the road. So flow across the road and speed. And each data point is a separate minute observation of speed and flow. So on this morning at 5 to 6 in the morning, the red crosses are connected by these red lines, and essentially what's happening is that speed is roughly at the legal maximum, around 70 miles an hour, and flow is building up through that encroaching of busy hour in the morning on a Monday morning on the M25. This is at a particular sensor close to the M3, going clockwise. What happens between 6 and 7 a.m. is the yellow line segments, and really in a matter of a couple of minutes there's this rapid transition between a free flow regime at the top there, where speeds are roughly, as you might hope, and roughly constant, and then there's a transition into this congested regime, which persists actually for quite a few hours through the morning. And during this congested regime, speeds and flows are varying minute by minute. This is the stop and go wave. Speeds are rather low, so journey times are high. Speeds are low, so fuel consumption's not so efficient. There are more minor accidents from tiredness and weariness of the speed fluctuations and so on. And also flow is not near the maximum flow that the road could support under those conditions, which might be 8,000 rather than say 4,000 or 5,000. So there's a loss of capacity in that as well. One way to understand this picture, in fact, is to think about the gradient of a straight line. So that would be of slope, speed divided by flow. So actually that's the inverse of density of cars. So as the slope decreases, the density increases. So think of a slope that's near vertical. That's low density of cars, obviously. When very early in the morning, there's low density of cars, people are not getting in each other's way, people are proceeding at the speed that they wish to. As the density increases, that's to say as the slope of that line decreases, there's a kind of critical density of cars, which is where it intersects with the yellow region. And as you go through that critical density, then it moves to this congested regime, where the free flow of cars has been disrupted by their high density, and that causes lots of ongoing congestion and issues. I was also interested in looking at some of the sort of macroscopic properties associated with this data. So what is the overall performance of the road? So just to put a couple of bits of terminology for that. So each road segment of, say, 500 metres has a loop detector. So for each segment and for each minute, there's a measurement of flow and speed. So for each segment and each minute, there's a vehicle miles travelled, VMT, which is just that volume of flow, that quantity of flow, times the length, let's say 500 metres. Associated with those vehicles is the speed of the vehicles and the time of travel. So the vehicle miles travelled divided by speed of vehicles, which again is one of the measurements, gives us the vehicle hours travelled. This project was part of a project funded by the Department for Transport, and they have a kind of reference speed, which is on this type of road is 67 miles per hour, to do with one of their then PSA 1A targets. So if one thinks about the vehicle hours travelled that would have been taken if everyone was travelling at the reference speed rather than the actual measured speed, and looked at the difference between the vehicle hours travelled and this quantity here, then you might associate that to the vehicle hours delay. So those three quantities, vehicle miles travelled, and vehicle hours delay, are all readily computed from this raw data of speed and flow measurements. And the way I thought of this, or I think a good way of understanding this, is to think of the vehicle miles travelled as the demand on a system. That's the demand offered to the system. Actually, that system is the road network, and the road network is a congested resource. So think of this now as a sort of a queuing problem, and this is the input load, the vehicle miles travelled, how many vehicles wanting to take those journeys. But the vehicle hours travelled is the performance of the road, how much time was spent making those journeys by those vehicles. So one is the input and one is the output. And if it's a congested resource, as we've seen many indications of it being congested, one would expect there to be some saturation. As the vehicle miles travelled increases, there should be a saturation which causes the vehicle hours travelled to increase. So with that in mind, the obvious thing to do is to draw a scatter plot of these two quantities. So on the left-hand side, I'll just talk about the left-hand picture for me. This is the vehicle miles travelled on particular journeys, particular days, sorry, from the multi-year data set. So these points here show a saturation effect, a rather clear saturation effect, as the vehicle miles travelled loaded on the road becomes around this level, 350,000. Then the vehicle hours delay just is increasing very considerably. So there's a saturation effect. And in fact, a very crude MM1 model might fit the red line to that type of data. So thinking of it as a queuing model or congested resource is something that's very consistent with what one sees in the raw data. Another way of visualizing those sorts of correspondence between demand and response is the following. So one could look at the vehicle miles travelled and vehicle hours travelled over a daily profile. So the forgive me for having two vertical axes. So the right-hand vertical axis is the vehicle miles travelled, which is the black dashed line. So as the day unfolds from 5 a.m., 6 a.m., this increases into a sort of a burst of demand on the system, vehicle miles travelled, which peaks around 7 a.m. or just before 7 a.m. And then it tails off through the morning. That's the demand on the system. But we saw the system was a very congested one. The response to that was a very poor experience for motorways, very poor usage of the road capacity. The flows were rather less than the peak capacity. And the red envelope here is the vehicle hours travelled. So that's the response of that system. As you load it with the vehicle miles travelled, the response is the vehicle hours travelled. And that increases along with the demand, but because of the very inefficient use of resources that persists thereafter, actually it's high for a long period, doesn't settle down until much later in the morning. In fact, if you compare that with the ideal vehicle hours travelled, that's to say what the vehicle hours travelled, where if everyone could just drive at 67 miles per hour, whatever the car density, I don't recommend that as a practice, by the way, but if only one could do that, possibly we will do that in autonomous vehicles, literally, if only one could do that, then in fact the trajectory would be the synthetically constructed blue one, okay, which would relax as the demand on the system relaxed around the peak of 7 a.m. And so the difference between those two envelopes, the red bit that's above the blue bit, is the vehicle hours delay. So that's the waste of everyone's time associated with the system operating in a sort of less than ideal situation. Okay. On the basis of the numbers I looked at over that southwest quadrant, I put the difference between those two envelopes at roughly a quarter to a third of all the vehicle hours travelled are associated with delay. So that's an enormous number in terms of, let's say, GDP. Okay, so that's quite a bit about the loop detectors, and I found that a very rich source of mathematical models, the queuing ideas, just the visualization is extremely helpful. Another source of road data is one that we looked at in the computer lab in a project, so-called Time project, which had access to the GPS traces of the buses in Cambridgeshire. And in fact, it was almost near real-time access to that data. So the GPS receiver in the bus is communicating its location back to a central server using, in fact, a GSM channel, I think, in those days. It's not as good quality as we would expect, perhaps, from modern GPS. So it was bus locations were plus or minus 30 meters, and the timestamps were taken roughly every 20 or 30 seconds. But nevertheless, you can see clearly trajectories of buses very closely aligned with road maps. Closely aligned because of that plus or minus 30 meters, but the natural thing to do is a road snapping technique. So I'll jump to 2 slides. There are lots and lots of visualizations of this data. I've just picked a couple of them which I think are particularly nice. And when we were doing this, we were liaising with the local bus company, Stagecoach, and one thing that came out quickly in discussions was, well, what's the journey time of buses? What's the daily profile of journey times? And I was a little bit shocked that that wasn't a sort of known thing, but anyway, it's something you can, with quite a lot of work with the data, it was easy, at the end, it was easy enough to extract journey times. So these are journey times of buses inbound to Cambridge on one of the northern routes into Cambridge. Each dot is a journey time, and the journey time is associated with a start time for the journey. And one can see that journey times around 8 and 9 o'clock can be quite variable, and then they settle down to lower levels here throughout the rest of the day. So this is inbound traffic in the morning. The ribbons are associated with a quantile regression technique. So the ribbon is the 10 to the 90th percentiles, and the red line in the middle is the median. So think of these as, those of us who are parents, we all know the newborn baby charts, which give percentiles of growth of babies' height and weight over time, and this type of quantile regression is used here too, where instead of growth over time, it's the start time, journey start time. So I think this is a nice visualization of the queuing underlying this. So it's a congested resource. The response to the busy hour is that median journey times increase considerably. But notice also that the ribbon increases considerably, so the variability in journey times is also much larger. And that's something we expect from queuing models, where the mean and the variance of the number present in MM1 queue both go to infinity as rho goes to 1, as the intensity goes to 1. So that's a very nice, clear story about the busy hour. In fact, the bus company were very pleased to see that, because they didn't want to be accused of poor journey times for any other reason, I think. Whenever I speak about this in audiences in Cambridge, everyone will ask afterwards about school journey times. So we separated out weekdays into school days and non-school days. And so the school days on the left, you get all the mess. And on the right, everything is much calmer. Okay. I think these visualizations were really helpful in communicating, the value of the data, sensor data, using sensor data, and engaging with an audience, both the bus company and with users as well. I won't spend any more time on this now, except to mention that with the loop detectors, we were looking also at journey time prediction algorithms for algorithms that underline the say the signs on the motorways that say 18 miles, 18 minutes, that type of thing. And also the GPS speed data, so speed of buses, use that as a heat map over your map. It's really fascinating to look at, say in Cambridge, if you get as we did on one occasion, a lorry fire on the Girton interchange at the northwest corner of Cambridge, then the consequences of that in the speed map, the heat map of speeds on the map of Cambridge are dramatic, and you see masses of consequences of that around Addenbrooke's, so which is in the southeast corner of the city. So the knock-on effects are very easy to visualise from this sort of data. Okay, but I'd also like now to switch gears and talk about energy networks. This is joint work with Stan Zachary and James Cruz and Rui Carvello and Andre Bijan over the last few years, also Frank Kelly. And the first problem that we were looking at was the problem of balancing demand in an electric grid. So this is a cartoon version of that balancing problem. So the idea is that you have thermal generation, also maybe nuclear generation as well, coming in on that left side. There's demand for energy given by households and industry and so forth. Increasingly, as we decarbonise the electric grid, the wind power and other sources of renewable power will also be introduced. But of course, as we know, wind power is quite variable. So the idea of this balancing was to help make this equation hold. So within an electricity grid, the demand for energy has to exactly balance the sources of energy, and that can be through conventional generation, so it's thermal or nuclear, wind generation, and any storage that may be associated with this network, the grid network. So the change in storage can also help balance that equation. So the change in storage shown here would be through a pumped hydro storage system. So for example, in Norvik there's a pair of reservoirs where at some time of day the water can be pumped uphill into the upper reservoir, and then there's a turbine waiting to generate electricity if the upper reservoir is emptied through it. And so in that way you can take energy out and put energy back into the grid. On quite a large scale, it's a very useful system. It's there essential for if a nuclear power station like Sizewell should shut down immediately, then you need to adjust the balancing very rapidly. So it's a very essential part of the system, but it can also be used to try to get the balancing to cope with adjusting thermal power in regards to wind power. So thermal power is difficult to adjust quickly. It has to be adjusted maybe several hours ahead. So let's look at some data. So we had some data made available through National Grid, who are supporting us on this project. So first of all, in the top time series is the pattern of demand, the aggregate demand in the UK over a number of weeks, 4 weeks or so. And you can see that actually there's quite a regular pattern. Obviously it's seasonal as well, but there's a regular daily pattern we can observe there. And National Grid are supremely capable at forecasting demand to quite high accuracy in the grid. The dashed line below that is, well, it's not exactly wind generation, it's actually a scaled version of the wind generation. So this is a scenario where wind generation has been rescaled as if its peak capacity was 24 gigawatts, which is one of the proposed future scenarios for wind. So it wasn't generating at that level in 2010, but let's scale it up as if it was generating at that level. And so you can see that's quite variable in relation to the variability of the demand series. And so the difference of those two is something that's got to be very carefully managed if we're to balance the electric grid precisely as we need to. Okay. So obviously both demand and wind are variable, but wind is far less predictable than is demand, I would suggest, and obviously wind is essentially uncontrollable. We can't turn the wind up. There is some possibility to turn the wind down by spilling it through turning the blades, but we certainly can't turn the wind up. And this is a very nice reference by Sinden on the UK wind as a resource for electricity, so discussing the variabilities. So I'll briefly describe some of the things we were doing with this. So as we try to, let's say, forecast the wind a few periods, say n periods ahead, say 4 periods ahead, say 4 hours ahead, in order to here and now adjust the thermal so that we can bring on the conventional power stations, we need to predict the wind. Well, we may not get all that right, and so there's a possibility that we might spill some wind. That's to say, more wind is produced than we were expecting, and we can't put it into storage because the storage is full. Storage has a capacity. It might have actually capacity in two senses. It has a total capacity, which we may be exceeding, or it may be that we can't put it in fast enough, and these are called ramp constraints in this context. So there'll be a ramp constraint perhaps for how fast you can put energy into storage, and also how fast you can pull out from storage. So some wind may be spilled. On the other hand, if your forecasting is such that you haven't got enough storage, you haven't got enough energy in storage, or you can't pull it out fast enough, then maybe some demand is not met. Okay. Now, in this case, we're scheduling the thermal demand, say 4 hours ahead. So let's envisage that there is also gas fast response system as well that can respond much more quickly. And so the fast response system will then take over but use gas-fired power stations to meet the demand. So the question is, which of these two things is happening? Are we spilling wind? Are we not meeting demand and then relying on the gas? So how might we do that? Well, first of all, there's a prediction problem. We need a predictor for the wind. Okay, and there's much written about that. For example, in the reference I mentioned, we use a relatively crude form of estimation for the wind. Also, how are we going to control the storage? Should we be putting excess energy into store, or should we be using less thermal power to make up the difference? So perhaps a simple strategy would be, let's try to maintain the storage level at exactly half. So given our prediction of the wind, given the ramp constraints, given the total amount of storage currently in use, let's try to drive the storage towards the level of a half. So in this picture here, in the first week or so, it looks like the wind is very low, and so we haven't got a lot of problem about forecasting the wind, and forecasting it as low and persisting as low is very successful, and we can basically track the level of storage, which is the top graph here on the lower panel, at around 5, which is half of the maximum 10. But as the wind kicks in at the middle of that top graph, then the storage actually fluctuates quite considerably as we're trying to do the balancing, as well as the wind changing in these patterns. And so occasionally wind is spilled, as shown in the middle graph, and occasionally demand is not met. That's to say, demand is met by a fast gas generation rather than the thermal. So I need to finish very briefly. So a nice thing one can do is then adjust that target threshold, let's say from a half, either decrease it or increase it. If we decrease it, then we're aiming to keep the storage rather empty, close to empty, in which case we won't tend to spill wind so much because we'll have places to put it. On the other hand, if we keep it nearer to full, then we're less likely to not meet demand by thermal storage because there's energy we can pull out of the storage system. So in the left-hand panel, this is a situation where in fact there's no ramp constraints, and so if we just look, for example, at the green curve, on the green curve with the red star, that's corresponding to keeping the storage as best as possible at level half, and if you go to the right, then what's happening is the trade-off is that the wind spill decreases, but the horizontal axis is showing the participation of the fast ramping. So that increases as the wind spill decreases, and vice versa. I think I should wrap up there. So this was a model of storage to cope with the balancing. Other work that we've been doing is looking at that storage from a sort of arbitrage type situation. So with differential prices at different times of day, then maybe the strategy is to pump the water uphill when the prices are low, and sell it back to the grid when the prices are high by passing it through the turbines. So models of that. And also quite recently been looking at models for, again in an electric distribution context, models for charging of electric vehicles, which I think is a very nice mathematical problem about the allocation of those resources in a distribution network. But I think there's nice connections with transport too. So understanding the way in which electric vehicles are used might, for example, suggest patterns under which we could say charge taxis, fleets of taxis. Could taxis charge successfully by charging at, say, taxi ranks and things like that? So there are nice connections between this transport area and the energy area, and some of those are exploring currently with the Alan Turing Institute project. So I need to wrap up there. I think I'm on my 5-minute limit, so thank you very much.
Let's thank Richard very much. We do have a couple minutes for questions before I introduce our next speaker. So, yes.
Thank you for a very interesting talk. The transport data, isn't it non-stationary if you go back to 1997 or 1995?
Over what sort of timescale?
Because the vehicles have changed, the destinations may have changed.
Oh, absolutely, of course, yes. So
shouldn't you break it up into different periods and analyse it over a shorter time period to see what those differences.
Yes, so I don't think any of the graphs I showed you had, maybe I said multi-years, but I don't think I meant multi-year. So I think there was a 1 year slice that was used in the saturation picture. That was my mistake, sorry. But yes, there are patterns of traffic, and indeed, as the recession came in 2008, the levels of traffic decreased considerably, and actually congestion decreased too at that time because of the economy suppressed traffic. Absolutely, yes.
Yes, I was fascinated by your analysis of the M25. Did it allow you time or material to assume anything else about the M25, or was it just that Surrey was particularly rich with those detectors?
It is the case that it is richly censored with loop detectors in that area. I have looked in other places, and others have looked in other places too. So it's a system that's, I think, rolled out over quite a substantial part of the strategic road network now. But the examples I showed were all in fact, all clockwise on the M25, southwest quadrant.
Just wondering, do we listen to the radio or come to your website for planning?
Okay, well that would be a very nice service. I think we're nearly there. I mean, the data I was working with was in this just raw dump from the incident detection system, but now it's all cleaned up, nice polished XML formats near real time.
Very interesting.
Yeah. 2 more questions and then we'll stop. Go ahead.
Yes, thank you. It's very interesting. Can I ask you about the speed flow diagram? I love that change of phase from non-congested to congested. Was there a critical value, and did that critical value change over time or over location?
Okay, so there certainly is a critical value, as I suggested. In fact, the transition seems to be over just a couple of minutes, the transition between the phases. I forget the units, so I remember the number was about 39 point something, but I can't remember units here and now. But does that number vary? So I haven't really got a concrete answer to that. I'm sure there is some variability with that. I think the critical density is going to be sensitive to, let's say, whether the road is straight or curved, whether there's an incline, all sorts of civil engineering aspects, I'm sure.
Yes, I mean, I'm involved in the European heating project, and my question is how close, I'm very interested in your first bullet point there, because of the Gothenburg Energy in Sweden, the economists who are doing the pricing, the buying, work extremely closely, in fact, in the same floor of the building, with the engineers who are controlling the power station. So I wondered how close that synergy is between the economic side and the engineering control side in these sorts of projects.
In these sorts of projects, well, I'm very sympathetic to both those aspects. And I think engineering and economics are sort of on a spectrum, really. Yes, I think people are very aware of the economic side of this. In Cambridge, there's an energy policy research group which is very active in this area. They're very active, very interested in these sorts of problems and other related problems in the energy markets.
All right, let's thank Richard again. It's great to have you.